Okay, so this is our maneuverability design and sort of analysis of canoes. So we're gonna start off with some kind of like math-heavy equations to define the motion of a canoe, and then we're gonna sort of apply some of that theory into the relations of each other and how they work, and then we'll do we'll talk about how we model that, and then we'll actually show how we do it in SolidWorks. So basically, the first thing that we are going to talk about is the equations of motions with respect to Earth. So here we have a great diagram that shows the coordinate system with respect to Earth and with respect to the boat. So assuming we have like an arbitrary origin somewhere on Earth, and we have like this x-axis here, and we have the y-axis here. Actually, let's use the highlight button. And we have the boat that just moves along, and it has its own axis with its x along the longitudinal axis and the y along the transverse axis. And so obviously this boat like can turn this way, and then obviously the axis of the boat kind of changes with respect to the Earth axis. So we will end up having to convert some of the equations of motions that we have in the Earth axis to the boat axis, which we'll kind of describe briefly about. But knowing this is kind of important. Yeah, so first of all, if there's an x naught or like a y naught, that's obviously with respect to the Earth axis. If it's just x and y, then it's just going to be with respect to the boat axis. We have u and v. So u is the velocity, or I guess, yeah, it's velocity in the x direction of the boat. And then v is the velocity in the y direction of the boat. And then we have the drift angle, which we'll talk about. And then the phi angle, again, which we'll also talk about a little bit more. Or psi angle, sorry. Anyways, so we have equations of motions here. So that we concerned are for maneuverability. There are obviously like heave, pitch, and roll, and other translations that aren't discussed here, but we have these couple that we care about for maneuverability. And yeah, so basically these are forces or in moments. Nothing to be too scared about. Basically, x naught, right? So we can just take a look at this. So with respect to Earth, x naught, the movement of the boat in this direction is simply the mass of the displaced shape. So m is mass, and then this little delta is going to be your displaced volume underneath the water. Obviously, you have a part above the water and underneath the water, and we're only worrying about the amount underneath the water. And then x here, we'll change the notation later, but the x obviously is to position, and then a single dot denotes velocity, and double dot denotes acceleration. And that is, again, OG, meaning with respect to Earth. So this is basically the force in the forwards direction. The force in the forwards direction with respect to Earth, and that's surge. And then the y direction, that's going to be sway. So that's like down, it's like sideways. And then n is the yaw moment. So like about the origin, we have I and psi. IZ is pretty much, some of you might not have learned this, but it's going to be the second moment of area, which is the ability for a body to resist rotation. Yeah, and then side, that was your yaw angle, and basically your that is your angular acceleration. Yes, there you go. So basically how fast you're turning or rotating about this axis. So we can break this down into like these components specifically, like these specifically. And so we'll start with velocity. So x velocity, x dot OG is velocity with respect to Earth in the x direction, and that's u cos psi plus v sine psi. So pretty simple. I'll just introduce it a little bit here, but then we can just like quickly move on. It's not entirely too important. We're just trying to get to the theory here. So basically, how you'd look at this is if you had like 90 degrees here, and then this is your sine angle. So obviously this is opposite. This is your hypotenuse and adjacent, and then you have, yeah, okay, and then so if you wanted to figure out in the x direction, you just do your cos. That's not too difficult there. So basically, you just break up the angles like you normally would, and for sine, you just do like a similar sort of angle thing. Basically, this is 90 degrees. So then, if I want to translate this psi, I just do 90 degrees to psi. So then, if I had 90 degrees here, this would be psi, and then you can still figure out the v direction. Anyways, moving on. So if we then just simply do some simple differentiation, we can get the acceleration. If you're familiar with the trigonometric differentiations. And then after that, we can just plug all these values back into our initial equation of motion up here. And then we're going to get something that looks like this. Now, we want to convert that to the ship fixed axis. So then we're going to need to transform this. So we're going to create this x and this y, and then translate that, transform it, and so we need to figure out what x and y is. Yeah, so basically, the next step is to simply, plugging into the previous equations and simplifying gives the equations of motions in the forces, velocities, and accelerations measured in the ship fixed reference frame. So we're gonna do some simplification here that the psi, we will never have like positioning. So we're getting rid of our dots here, and we're just gonna say that our velocity is no longer has a dot on it. It's just gonna be u, and then so therefore our accelerations are just gonna be u dot or v dot. And then our psi, or our angular acceleration or velocity, is going to be denoted with r, or r dot. So then if we plug that into here, we get this. And then after that, we need to solve for x, y, and n. Basically, we wanted to find, we have it defined here, but obviously they are a function of a multitude of different forces, velocities, and accelerations acting on the boat. So we'll actually define what those are. We will care about two of them, but there are a multitude of other ones that are not too important. So the first is hydrodynamic forces acting on the hull and appendages due to ship velocity, acceleration, rudder deflection, and propeller rotation. For us, obviously, we don't really have propeller rotation. So here are a couple different things or different forces and situations that cause these forces and affect X, Y, and N. Again, that's our surge, sway, and our yaw moments. And then we also have inertial reaction forces caused by the ship acceleration. This is actually pretty important too. It's kind of similar to our stability sort of lecture that we talked about. External forces having an effect on some of the internal forces and sort of a bouncing sort of moment. So same thing kind of here, but instead of like tipping, we'll talk about some of the translational effects. So basically we can say that the sway, the surge, sway, and yaw is a function of u, which is the forwards velocity in the x direction, the acceleration in the x direction, the y direction velocity, the y direction acceleration, angular velocity, and angular acceleration. Yeah. So to actually solve for these, we will need to get a bit of a review of Taylor series. So if you remember, what that is that if the function of a variable x and all of its derivatives are continuous at a particular value of x, say x1, then the value of the function at the value of x is not far removed from x1 can be expressed as follows, which is shown here. Then obviously if we're engineers and we like to simplify things, so we're just going to ignore the higher order of x because they're just small. And then we can just rewrite that to something like this. And then if you have multivariable equations, so if you're not just a function of x, but let's say you're a function of x, y, x and y in this sort of brief example here, then you're going to have to do some partial differentiation. Not sure if some of the first years here have done it, but great. So basically, this would be sort of the general equation to do that. Now, trying to apply that to our case, right? So our fx having all of these effects, we plug that in and we're going to have something that looks like this. Yeah. So it's kind of long, but yeah. But we'll end up simplifying a bunch of these different terms in the sort of next moment here. So yeah, we're going to have a couple of assumptions. So we're just going to say that u1 is equal to just this big U, which is not really assumption, it's just our notation. But then we're going to say that v1 and r1 is equal to 0, assuming that we're just going to say for a straight line stability, just assuming you're just moving in a straight line, we're not going to have any rotational effects, we're not going to have any sway effects or sway velocity, right? So these are sway and angular velocity. So we're going to set them to 0, and we're also going to say that we're just moving at a constant speed forward, so our accelerations, all our accelerations are just going to be 0, and yeah, and then we're also just going to say because of that we will be in equilibrium, so all set to 0, and due to symmetry, our boat, I hope everyone's canoe is symmetrical. If not, they're doing something wrong. Then due to symmetry, our sway forces are going to be 0. So that's our sway with respect to just moving forwards is 0, and our sway force with respect to acceleration in the forward direction is going to be 0. So basically, we're just saying that if you're moving forwards and accelerating forwards, there's no sideways force, which should be true. Then we can say, essentially, once we do all of that, we can simplify to these couple of equations here. So our sway, surge, and yaw is shown here. Yeah. Now so we finally solve for the y, x, n, and if we plug that all the way back up to these the equations, basically up here, and then just shove everything to one side, we're going to get a final sort of equations here shown here. So yeah, a little bit complicated, but yeah. And then after that, we're going to non-dimensionalize it, in which case it doesn't really affect the yaw moments, but some of the terms sort of disappear in the surge and sway. Great. Okay. Cool. I know I kind of just sprinted through all that math, but not entirely too important. As we'll talk about relations that occur between them that we would really care about when we're designing. Like, we are for sure not going to do any hand calcs on this. But yeah. Anyways, we'll discuss briefly about the effects of the rudder and sort of how the notation of the rudder, and then go into the cases. So the rudder is assumes So when we put that in, so it's gonna look like this. It's gonna have like an opposite sort of effect, and yeah. So the notation is if you have a positive rudder angle. So this is a rudder angle. Delta is your rudder angle, and if it's measured for against a longitudinal axis. Positive, going from I guess aft towards port. Right. So this is the back of the boat. So this is stern. And then this is the port. So moving from the stern to the port is a positive sort of direction of your angle. And that is naturally, as your water comes along here, it's going to force your boat to turn in this direction. So the positive sort of, again, N is a moment. So N with respect to your delta, N with respect to your delta is going to be, oh no. I forgot what this Greek letter is. Whatever. Anyways, N with respect to your drift angle is going to be in the counterclockwise direction, which I'll briefly talk about is kind of the opposite sort of notation of normally N is in this direction for everything else. Yeah. All right. Cool. So I think that's really everything. But yeah, so basically I ran through a bunch of different variables and stuff like that you might be confused about. So let's go a bit of a review to help everyone sort of understand things. So we have our forces and our moments, and we're actually going to ignore surge because the effects of surge on the maneuverability is actually not too important. So we're just going to kind of ignore them. And so we're going to have our sway, which is our Y, and our yaw, which is an N. And they are forces and moments, right? And they are affected by the velocities and the accelerations, which are shown here. So you have U, which is the velocity in the X direction or a longitudinal axis, and V, the velocity in the Y axis or the transverse, and R is the angular velocity about the Z axis. And if there's a dot above it, then that means they're the acceleration of them. So yeah. So and also yeah. So the forces and the moments are affected by the rudder angle, which is denoted by this Greek symbol here, and it is the angle between the x-axis and the rudder, positive towards the port side. And then we also have a drift angle. Basically, boats like drift all the time. They never always seem to sort of head in the same direction that they're pointed to, oftentimes, especially when you're turning. So that's essentially known as the drift angle, is the direction you're heading, you're actually moving, and then the angle between that and where your ship is actually facing in the longitudinal axis. And then so we have a bunch of derivatives. And so here we have, I just denoted, basically we have our sway force with respect to, so basically the rate of change of our sway force with respect to the U, which is the velocity or acceleration in the X direction. And again, so basically we have derivatives of all of these, and how they affect your Y and N, your sway force and yaw moment. So if you see these, that's basically what this means. Great. Now, moving on to sort of understanding the relations is we'll go through a couple of different cases and see how they sort of affect. So case one is, imagine if your boat was having a transverse acceleration, a positive transverse acceleration. So positive is kind of, I denoted the notation in the first sort of slide. Positive is obviously towards the starboard. So if you started moving your boat just literally sideways somehow, and you're accelerating that direction, what exactly would occur? So you would have a sway force with respect to that acceleration, denoted as y sub v dot, and that opposes your transverse acceleration. This is kind of intuitive. If you push something in the water, obviously it's just not going to go there in the same sort of direction. There is some type of force opposing it. It's basically the water that opposes your movement. Yeah. So I guess in our stability, we talked about the tipping effects of this, but it obviously, the boat doesn't just tip. It also kind of translates a little bit in the water. And so this is the force that is resisting, I guess, you pushing it over. Yeah. So basically, you have your acceleration in the positive, and then you're going to have a sort of a sway force in the counteracting in this sort of free body diagram here. Although, yeah. So we can always say that the sway force versus the sway acceleration is going to be always negative. Yeah, it's always going to count, it's always going to be in the opposite direction. The next case is your angular acceleration. Kind of similar to the transverse acceleration. The angular acceleration is going to be opposed by your yaw moment, a reactionary yaw moment. So again, I guess this wasn't in the first slide, but the actual notation of positive is this. So it's counterclockwise. It's from the bow to starboard is positive direction of rotation. So if you had a positive rotation, positive angular acceleration, so positive r direction is in this direction, clockwise, and therefore your yaw is positive, then you're going to get a negative reactionary yaw moment that opposes that and wants to push the boat back that way. This is kind of intuitive. Again, if you, I don't know, are in the water, I guess, I don't know, you're lying down and you try to rotate yourself, the water obviously is going to push against you from rotating because you have to go through all the particles that are blocking you. And yeah. So we are going to get we're going to get moments opposing you in the opposite direction. And so it's always going to be negative. Yeah. And I guess you can also break it down here as it shows in this image here that you're going to have a local transverse acceleration depending on your sort of rotation axis, where you're going to have this. Basically it's this would actually denote this moment here. So if you literally took your triangular distributed forces here and then you calculated your I guess 2/3 here, it would be, that would literally be your moment of resistance here. Anyways, case 3 is sway velocity and forward velocity. So I guess if you're moving in a diagonal direction here, as denoted with V, capital V, you can break that down into your U and your small case v. Well, what are the effects? So obviously, it's sort of, as we kind of discussed above, any sort of velocity is going to be opposed in sway direction. So if you're moving your boat this way, so let's just ignore U for now, and we're looking at V. Any sort of V, we're going to get a natural sort of opposing force. Opposing force. And, But what actually occurs is your bow force, your bow sway force is going to be greater than your stern sway force. And what ends up happening is you're going to have a moment because of that. And that causes, and usually the bow is going to have a larger contribution. So you're basically going to start turning in a negative sort of rotation because of that. like this, your bow force is going to be greater than stern force. Usually, depending on the shape of your boat, it might be different. But for most cases, and for most canoes, it should be like this. Yeah. So basically, with your sway velocity and forward velocity, you're going to get a negative sway force and likely a negative yaw moment. But it can be positive if your sway forces in the stern are greater than the sway forces at the bow. Yeah. And so sort of that relationship is shown here. All right. So fourth case and the last case we're going to sort of discuss is the forward velocity and angular velocity at the same time. What ends up happening is basically, yeah. So again, positive direction here. So you're just accelerating this direction, and you're also going to be rotating quicker in the clockwise direction. Basically, what ends up happening is yeah. So basically, you're going to get a sort of a negative. Yeah. So there's going to be a negative moment contribution from the bow and the stern. If we break up this rotation here, so if we take like separate points in the bow and separate points in the stern and sort of see the different forces that are going to be occurring there. We're going to be moving in this direction and this direction. So if we break it up, basically, if we break it up, we're going to have this sideways velocity, I guess. No, or yeah, we're gonna get this sideways velocity, obviously, because we're turning in this direction, and so again, if we're going to have a sideways velocity, that's going to be opposed by some type of force in the negative direction here, as shown here. So we're going to be a force this way. And if there's a force this way, obviously we're going to have a moment about this sort of pivot rotation in the clockwise direction, which is negative. And if we do the same in the stern, if this body is like rotating, what? Okay, sorry. Computer's frozen a little bit. Okay, there we go. I'm back. If we're rotating, right? So obviously the bow wants to move in this direction, and then the stern wants to move in this direction. We're gonna get some type of velocity this way, which is a sort of a negative velocity, and a negative velocity. Then we're gonna get a positive reactionary sway force in the stern, and this is about this axis, so we're gonna get a positive contribution of the moment in that direction, right? So therefore, we're gonna get a negative moment both from the stern contribution and so the bow contribution and the stern contribution from the sway forces. Yeah. But because the sway forces are acting in sort of opposite directions, but they kind of cancel out. So they don't really actually do anything much. But what ends up really happening is your boat's just going to rotate in the negative sort of direction. Yeah. And these are some graphs to sort of show this relation. Great, so that was sort of the last case. The next part we're going to talk about is the turning radius equation. I do want to note that, I'm not going to discuss this because it's not entirely too important to canoes specifically, but there are 3 different phases of turning. There's like an approach, and there's like the beginning of the turn, and there's a constant sort of velocity, and you're no longer accelerating about some point. But that's not the case for a canoe, because you got your like front members prying or drawing, and then so is the guy at the back. So it's no longer is our rotation mostly controlled by the rudder. In a traditional boat, which is at the back, we're going to have contributions of forces all along the boat, at the front and also at the back. So we are actually not going to likely have some type of like consistent turning arc, which is the 3rd phase of your turn. But nevertheless, this turning radius is basically linked to that constant turning radius. It is basically noted as your like the minimum turning radius possible, depending on your boat shape, and your rudder angle, and the mass of the canoe. If you had a rudder in the back, but that is not the case for us. Regardless, we can kind of use it as a measure for, I guess, our canoes. Obviously, if a canoe had a larger turning radius, obviously, even though we're going to be turning it with paddlers at the front, it's still going to be harder if you than a canoe with a smaller turning radius. Anyways. Yeah, so there are a couple different strategies to reduce the turning radius. And which we'll sort of discuss. So, and there's actually like a 5th one, I guess. Yeah, there's a couple actually. There's a couple, but that is not sort of discussed here, and it might actually be specific for canoes, for us specifically, as we're sort of able to design a little bit more freely than some other boats out there. So the first one is decreasing the YV prime, which is, again, the sway force with respect to the sideways velocity, the transverse velocity. This can be achieved by decreasing the L to T ratio. And if you remember, L is the length of the canoe. Sometimes this value can be changed. It could be the length between perpendiculars, or the length of the water line, because that's really what is in the water and actually causing your resistances in the water. And then T is your beam. But this can be destabilizing, right? So how could you increase the L to T ratio if you made the beams a little bit narrower? And obviously, if you made the beam narrower, you would make your boat really unstable. Your metacentric height would obviously drop drastically. Actually, it would be a cubed value that you're decreasing your sort of metacentric height. So not exactly recommended, but we can sort of still decrease the YV in different ways. The next one is generally increase your yaw moment with respect to the sideways or transverse velocity. If this is negative, and that is literally always going to be negative for us. And this is a result of different bow and stern shapes. Changes could be made by cutting away the skeg and deadwood aft or increasing 4-foot forward. So what does that mean? Basically, if you had your canoe, let's actually draw 2 types of canoes. So you got your first type, which is literally, okay, this is a sideways sort of elevation view of it. And then you got another one here. Obviously, the second one is going to be easier to turn. Why? Because, okay, assuming that there's the same sort of length, which I tried to draw here, as you're trying to rotate, water has to pass essentially around the canoe or underneath the canoe. And if that is, and this is also assuming that you sort of had the same sort of water line. So your draft is the same. So the distance between the bottom of the canoe and the water line is the same in both cases. Then obviously, then you have, basically you have this area here that water can just like pass through quite simply. But in the top sort of case, that's not possible. The water sort of has to go around the backside of the canoe or underneath, and there's going to be obviously a larger area of resistance. So in canoe lingo, we're increasing the rocker. This is known as the rocker. So if you increase rocker, you just make it more curvy, and you just make it able to turn more simpler. You can have a full rocker, which means the entire canoe sort of has a curvature to it, or you can have like not a full rocker, where you have just the front and the back sort of curved, and then sort of a flatter type midsection. I would recommend the latter option. Usually I've seen canoes with a full rocker, and they are very sort of directionally unstable. Like they just can't go straight, ever. So I would recommend having some type of flat sort of section. The next option is to increase the N. The yaw moment with respect to the rudder angle. Right. So this can be done by moving the rudder as far aft as possible and make the rudder as efficient as possible. So rudder efficiency is not something we're going to discuss, but we have used this strategy in the past before. And this was achieved by increasing the beam width, length, or also increasing moving the beam sort of further back. And this enabled the helmsman to sit further back more comfortably, more stably, and just lean back and just like stick his paddle as far back as possible, therefore creating a larger moment arm for him to actually create or enable the canoe to turn. This isn't, I would say, a great strategy, as some of your resistances are going to be affected, particularly your pressure difference, your viscous pressure resistance is obviously going to be a bit worse. So I won't rely on this one too much, and making your boat a little bit wider for that to occur is going to have a bunch of negative effects. So it's not really going to help out too much. And the last option would be to increase your sway force with respect to the rudder angle, and that can be achieved with a larger or more efficient rudder. Obviously, a larger paddle is going to give you the ability to create a larger moment against the water and turn. But there are paddle rules, so yeah, up to your team to try to buy a better paddle. There's a fifth option. Obviously, if we just analyze this right here, obviously there's the ability to just shorten your canoe. If you made your canoe shorter, your turning radius is going to be obviously shorter. So yeah, the difference between a 20-foot canoe and an 18.5-foot canoe is pretty big. So I would say chopping your canoe is probably the most efficient way to decreasing your turning radius. And also, this is your inertial sort of effects with your mass. If you decrease the weight of your canoe, obviously it can not only turn faster, but it can also accelerate faster and just change direction in any direction faster. So if you made a lighter canoe and if you made your canoe shorter, those are also going to help. So after all this discussion, the next part is, okay, well, now how do we exactly get these values? How would I exactly get some of these values? And we're going to actually create some tests, or the tests that we created solve for the sway force and yaw moments with respect to the transverse velocities. And this is achieved by something the naval architects have designed called the straight line toe tank test. And basically, they just stuck a boat in a tow tank. Usually it was a model, though, so it was a little bit smaller. And they would, I guess, attach it to a string and just tow it along at a certain drift angle. And then they would measure the forces and the moments on the boat. And they would pull it on at a certain speed, which is denoted here as v, and they would break down that sort of sway force. I mean, I guess the sideways transverse velocity, quite simply with just some easy trigonometry, right? And they would also measure the moments as well. So how readily is the boat trying to turn? Yeah. Yeah. Basically, we don't 3D print our canoe and test it in real life, but we've developed a method to actually test this in SolidWorks. So, oh yeah. So basically, this test is by towing the canoe at a certain drift angle, and you tow it at some speed v, and then you just measure the sway force and yaw moment, and you test it at different drift angles to get some more data on your graph. So, for SolidWorks flow simulations, there's a couple different assumptions that we made to help us actually run it a little bit simpler. Yeah. So the basically, instead of us towing the canoe, we just leave the canoe stuck in its spot, and we just shoot water at it at an angle, and then we measure the forces and the moments when that occurs. And so the first sort of assumption is that we're going to ignore any of the free surface effects. And so a free surface is the interface between two different fluids. So in a canoe, we're going to have I don't know, it's not disappearing. Anyways, we're going to have the water and the air is a free surface. And between them, when at the canoe, there's going to be a lot of different disruptions there. There's going to be like spray. There's going to be water that comes into the air. But we're going to ignore those effects. Why? Well, we kind of discussed that, especially in a canoe setting, at lower velocities with respect to, like, obviously high-speed boats, wave making isn't that much of a problem. I'm going to pause real quick. So so basically, in terms of resistances, which this is basically reactionary forces and moments, which is resistance, the effects of waves at lower velocities, right? We're moving at like 3.7 meters per second, the low velocity. That's not going to really affect us that much with respect to like frictional forces and shape, like the pressure differences caused by your shapes. So I wonder if I can. Okay, I guess there we go. So we're going to ignore that sort of interaction with the water and the air, and we're just going to model the water. And we're not even going to model the water that occurs above the draft that you have designed for. The second sort of assumption to simplify things is the roughness coefficient. Or I guess, yeah, we just assumed a constant roughness coefficient of 0.4 microns. We just researched a value of concrete. Yeah. Initially, we had set it at 0, but we're gonna assume some type of frictional roughness. So yeah. And then we tested at 3 different drift angles, 45 degrees, 9 degrees, and 135 degrees, and then we just graphed those, and we were sort of able to see the sway force and yaw moments there. Yeah. So the velocity that we use is 3.7 meters per second, because that was our like sort of top sort of average speed over 100 meters, and so we're just gonna assume we're gonna analyze the boat right as we turn into a hairpin turn, right at the end of the 100 meters, and we're going in at 3.7 meters per second. So what are those forces which are the maximum forces that this boat is going to sort of experience. So basically, we're not going to, like, we're doing with respect to like the water being angled rather than the boat being sort of angled. So we kind of have our own sort of system developed here. In this case, we have our beta angle is with like off the forward sort of axis, and then we just measure that off from like 45 degrees, 9 degrees, and 135 degrees. And so for 45 degrees, the water is going to be shooting in this direction, and then 9 degrees it's going to be shooting in this direction, and the 135 is going to be shooting in this direction. And then we just solve for the water force, or the water speed in the x and y. And obviously we're assuming the water is not moving up and down, so z is just going to be 0. So when we plug into SolidWorks will ask for us for the speed of the water in x and y and z, and basically in our notation, naval architecture notation, that is our u and our v, and this would just simply be the speed, which I denoted as capital V, times our cos, and then our beta, which is our drift angle, right? So that would be your 45, 90, or 135. And because the water is going to be shooting sort of always from the right to the left, it's always going to be sort of negative. Yeah. And then that would give us this some type of force that's going to push us this way to oppose that that water. Yeah. Basically, I believe that is it for that. Now I'm gonna go into like how we actually do it in SolidWorks. If you get your model going, how do we actually use SolidWorks? Great.